Also, I want to tell you that I updated our little YouTube channel, and lectures up to Tuesday this week are all on that YouTube channel. And that's why I didn't send you the recording, because I posted it on the channel. So that's what I'm saying. Look at the YouTube channel. It is in there. YouTube channel for our class you can find in the in those links that I was sending to you, right? Let me see if I can get to it quickly. No, it's not here. So I need to find the syllabus, and it's there. So to go to the syllabus, I need to go to the, let's see. Get here. So again, I posted this recording on the YouTube channel. So now there are more recordings on that channel. So they're all in one place. That's why I didn't email it to you. Well, today's recording I will email, so you'll be able to get a link. But I updated the YouTube stuff, and that's why I can, of course, share this with you. So I just want to get to that channel quickly. So I can copy and paste this stuff here. This is, because I'm not sure where to find the link. It's in your emails. I kept emailing it to you pretty much on, was talking about this on daily basis before the midterm. And I asked you to save the link to, after you click on this playlist for trigonometry, what you can do is save it, click here. So this way you always gonna have access to it, because it looks like I keep answering same question again and again and again. So you can just get this link saved, and you will always have the access. So here's the link that I'm going to share this one, so it'll be easier for you. It's always a good practice to save links, because otherwise you're going to be asking me every time, and sometimes you might feel like doing something, and well, if I'm not around, you may lose that feeling of doing some work for the class. So the last recording is here. It's the last number, 14. So that's what we did last time. So you can see this solving of equations. So anyways, I just shared link with you. So please make sure that you bookmark it. Here's this star in the upper right corner. If you bookmark it, it's always going to be with you, this YouTube channel. But again, I will email you today's recording after we finish with this little lecture. So let me do the problem. If you have one in mind, you can just tell me which one, or I can select one, let's say 77 with tangents and secants. So one thing to realize that secant theta squared is 1 plus tangent squared of theta. That's Pythagorean identity. That's the formula. One of those at the end of the book that related to Pythagorean identities. So if you are looking at exercise 77 with tangent squared equals to 3/2 times secant, then right away you can utilize this formula because you have secant and you have tangent. So you just want to pull out tangent from this formula and replace it with a secant squared minus 1 is equal to 3/2 times secant. Of course, the equation with fractions is not very good for factoring. So what I can do is clear denominator by multiplying by number 2 every single entry in here. And then bring also that 3 secants to the left side so I can nicer factor that. So it'll be minus 3 times secant of theta, and then minus 2 is equal to 0. So this one I will factor, and I will get 2 parentheses. First we'll have 2 secant, and the second will have secant. That's the only way I can factor 2 secant squared, 2 times 1 secant. And looks like to get -3, I want to put minus 2 here and plus 1 in the first parentheses. The reason is when you put these terms together, you're going to have a positive secant, like middle product, and the outside product will be minus 2 times plus 2 is minus 4 times secant. You see, they collect and give you exactly what you need, -3. So the factoring techniques that we, I guess, utilized back in math classes, you can use quadratic formula to solve equation if you don't like to factor. It's longer, but I'm sure you can factor it yourself. So 0 is either one of these two factors, right? Because their product is 0. The only way they could be 0 if one is 0 or the other is 0. So minus 1/2 is for the first, and the 2 is for the second. Now here comes a little bit of a range of function secant, which is 1 over cosine. Actually, I better put it as 1 over cosine instead of bugging myself with secant. I will turn this to cosine, so that'd be a better idea. So 1 over cosine theta, which means that for the first one, cosine theta reciprocal is going to be -2, and that's not possible because cosine is in between minus and plus 1. So I just end up with only one little equation that I can write, I guess, on the other side. So we got more room here. So that will be cosine theta is equal to 1/2. Why is that? Well, because you could flip both sides, right? Cosine theta is going to be the left side, and 1/2 is the right side. So I need to solve this using my favorite circle approach. Cosine is on the x-axis. Cosine defined as x coordinate. So it corresponds to these two angles. So 1/2 has to do with pi over 3. You can check this if you want at the back of the textbook. So the other is minus pi over 3, but I'm not going to call it as minus pi over 3. I'm going to call it as 5 pi over 3. And that way I've got answers in the region from 0 to 2 pi. Notice that this group of exercises is not interesting because they all have just thetas. We were solving last time equations with 2 thetas, 3 thetas, but just hold on, we'll get there again. So it looks like I got 2 answers. And of course, I can write infinite solutions in such a way that we put pi over 3 plus 2 pi times k or n, whatever you like better, or 5 pi over 3 plus 2 pi k. So 2 pi is period for function cosine. So that's basically all we learned last time. And the advice was to somehow convert, if you have your tangents and other functions, to sines and cosines. So eventually I ended up doing it anyways. But you could have done it in the very beginning. But I noticed, and I wanted to introduce you with Pythagorean identity formula, which is a very popular one, actually. So I guess the more you see it, the better you feel about this Pythagorean identity. So eventually you're going to recognize. So whenever you have secant and tangent, the message is you can always turn this to some type of Pythagorean identity and work on that somehow. In fact, this idea opens us the door into the next sections. Next sections of this chapter will utilize more of various trig identities. In fact, that's actual name of this section, trigonometric identities. So we'll move to the next section. And here they are. Those identities are ones that we already saw. And the one that I just worked with is here. Pythagorean identity deals with tangent and secant squared. The other similar deals with cotangent and cosecant. So it's pretty much same. And the most popular is sine squared plus cosine squared is equal to 1. I'm sure that one you know already. Now there are also definitions of tangent, sine over cosine. It's reciprocal, so you flip and get cosine over sine. And also reciprocal of sine is cosecant, and the reciprocal of cosine is secant. That's what I just utilized, right? Secant, I wrote as 1 over cosine. So it is important to be familiar with these identities. In fact, this previous section already utilized 2 of them in the exercise that I just done for you. So it is really hard to say if this section come first or that new section, the one that we now in, comes first. And of course, reciprocal of cotangent is tangent and vice versa. Reciprocal of tangent is cotangent. Now, the other thing to realize is that such function as a sine is symmetric through the origin. In other words, if you rotate it by 180 degrees, you get the graph that is not changed. And that's why people say it's odd. And the other odd identity is 1 over sine, because 1 over sine is cosecant, and that will be basically hanging here on the top and there on the bottom, right? And so forth. So if you rotate it also by 180, it'll be the same thing. Well, cosine function, as well as its reciprocal, is even. So even functions, they are symmetric through the y-axis. So you can see that symmetric, if you put mirror along y-axis, then it's going to be called even function. I guess classic example is parabola. If you have parabola y is equal to x squared, it's even function. It's also symmetric through y-axis, and it's even, people say, because it's a even power of x squared. And analogously, if it's a cubic parabola, it's odd. So it's from this group. So these two are going to be even functions because, again, cosecant will be just a mirror image, not a mirror, just hanging on the cosine function. So that'd be those two. And tangent and cotangent are also both odd because divide odd by even, minus still remains. 1 minus means minus. So that's something we're not going to use too often, but it's good to be aware of. So it looks like these identities is what I already familiar with. So nothing new, just practice on this. So I think what I can do is just go to the end of the section and do exercises. I guess the plan for today will be to do a few problems, and that'd be all we need. Now, one thing, I don't remember if I told you, you should probably get email from the college this week or next week asking for evaluation. So every once in a while, they like to do student evaluations. In fact, I asked them for doing it because they usually give me back this evaluation sometime in November so I can see what happens and various other things, so what I can do to adjust my teaching and everything. That's the reason why they like students to fill those evaluations. So when you get that email, I'm not sure that's it's a college supposed to send it to you. Well, please fill this student evaluation. So I get some feedback. That'd be nice. You don't have to, and don't say you must do it. No, you don't have to, but it'd be nice if you can fill it. It should not take too long. So anyways, in the next section, there are various exercises and they're not equations. They don't say solve equations. What they say is take the example, let's say exercise number 19, and convert left side to the right side. So if you're given cosecant theta multiplied by cosine theta, question is, how can I possibly make it equal to cotangent of theta? Well, whenever we have cosine and cosecant, advice is always rewrite cosecant as 1 over sine. So I start on so-called left side, and I can produce right side. So that's the plan for this exercise. So if you start it on the left side, and if you put cosecant as 1 over sine, and you multiply it by cosine of theta, then notice that this is equal to cosine over sine, and this is exactly what my cotangent is. Cotangent is cosine over sine, so it is equal to my right side, which is cotangent. So I started on the left side and I produced the right side. Sometimes you can start on the right side and you produce the left side. The idea is I always start on the side which looks more complicated. For example, if I look at the side, which looks like pretty much all of these, I will start on the left side. Like, for example, if I take problem number 38. Turns out you don't have to do all of them because when it gets towards the end, the problems get pretty involved and time consuming. I can do one from those just to illustrate, but I don't expect you to do problems that have lots of denominators. You could probably stop somewhere at this level at exercise 40 or so, because I don't think you will see them on my tests. But if your goal is to take more math classes, then you can enjoy it a little bit more. But in the calculus, we don't really get any farther anyways. Maybe in differential equations, that's a little bit more involved in algebra class, but we don't really get very deeply into this. So let me do this cosecant minus exercise 38. So I just selected one at random. If you like an exercise, you just tell me which one I can try to work it for you. But again, I want to warn you that some of them might be time consuming, but they're doable. So anyways, when I see this cosecant minus cotangent, and my goal is to produce this fraction, well, I don't think I want to work with this fraction. I want to produce it. So I'm starting on the left side of this equation. It's supposed to be L. And I write cosecant as 1 over sine, right? And letter U here. And cotangent is cosine over sine. You can say, oh, if you wrote it using sine and cosine, then you can right away put them together. So your denominator is going to be sine. Maybe I better use the other side. I get more room this way. In fact, these exercises that follow, I probably should do on the separate board because some of them take in little room. So just like you call your variables, you can call it as X, you can call it as Y, you can call it T, time, right? Sometimes in physics. Same here, it doesn't matter how you call your variable, theta or U. In trigonometry, they like to use theta. For some reason, like historically, it's like it's supposed to be Greek and Greek alphabet, and that's why we get that. But other than that, it doesn't matter, really. Sometimes they call it as U, sometimes it's theta, sometimes it's a T. It's pretty much all they have here. So I'm looking at my goal and I see the sine is supposed to be in my numerator. So what should I do to produce sine in numerator? Well, turns out here's a trick. The Pythagorean theorem. Sine squared plus cosine squared is equal to 1. So if I bring the cosine over to the left side, I'm going to get the way to produce sine. It's actually a standard trick, so I just want to show it to you because lots of problems will be using it. So I can factor this right side with difference of two squares, 1 minus cosine and 1 plus cosine. In other words, if I give numerator a factor 1 plus cosine, I will be able to get closer to what I need to the sine. So if I multiply and of course divide my fraction by exact same thing, so this way my numerator will actually boil down to sine squared on the top, right? And on the bottom, I already have a sine, so it's gonna cancel. See, I got used to put this theta, and they put letter U in this exercise. Well, you can put theta everywhere, so it doesn't bother you. But anyways, so after I produce this multiplication, then I can cancel by one sine, and I get exactly what they have here. So they just want to do some algebraic manipulations. And usually we start on the left. Sometimes we will start on the right, like in exercise 53. I will start on the right because I think I can work out that piece and then produce the left side, because you need to be very creative to pull something out from the fraction. And that's why I think that for exercise like 53, I better start on the right side, and that way I should be getting the left side. Even though it doesn't matter, because you could just start on either side and produce the other side. For problems that are more involved, probably by the end of this group of exercises, sometimes you have to work on both sides simultaneously. So you need to start on one side of your identity that you're trying to prove and do something, and then when you get stuck, you work on the other side, and then you see how you can produce what you just got there. So anyways, that's a secant minus tangent. I already know that secant and tangent will be involved in one nice Pythagorean identity. That's why I'm going to be working on my right side. So I say my right side here is going to be equal to, I'm going to square. So I'm going to take this parentheses and multiply it with itself. So I'm going to get a square of first term. The last will be a square of the last term of tangent. And the middle will be 2 times secant tangent. Not enough room. I should have used the piece of board. So anyway, secant squared is equal to 1 plus tangent squared. Can I use it here? Notice I have secant squared and tangent squared, and then also secant and tangent. So it looks like I can't. I got stuck. See, that's why I'm saying that the problems beyond 40 getting a little bit more involved. And that's fine. You get stuck, you get to the dead end. So it means you better start it differently. How I can start it differently? Well, I can write it all in terms of sines and cosines because my goal is to get sines and cosines anyways, right? And I told you that's the universal method. So secant is 1 over cosine plus tangent, which is a sine over cosine. And that was a very good idea, right? Because you see now that you have a same denominator. And after you put these two fractions together, you're going to square. So you're going to end up with a cosine squared, cosine on the bottom, 1 plus sine on the top, and then a squared. So don't want to hurry. Okay, so after I square, let's see what's going to come out. I just want to clear that out. So denominator will be a square of my cosine. I just need to be careful because I forgot to put square around my denominator as well, right? Because it says square this whole thing. So my numerator will be 1 squared plus 2 times 1 times sine, and then plus square of sine, right? And for the denominator, I have a cosine squared. So now the question is, how can I get this thing, right? Because that's my left side, that's what I'm trying to produce. So I always want to look at my goal, and I notice that cosine squared, since everything is in terms of sines, should be also turned into sine, and we know that this is a 1 minus sine squared, right? Okay, that's good to know. So I don't think this numerator stuff is what I really can work with, because looking at numerator that I need, I just rather have 1 plus sine squared, because it might be possible to cancel it. See, so if I have 1 plus sine theta squared, which is 1 plus sine times 1 plus sine, then looks like we're done. 1 plus sine times 1 plus sine is on the top, and what's on the bottom? How can I factor my denominator? Do you see that? It's a difference of 2 squares. It's 1 minus sine times 1 plus sine, or vice versa. So you actually cancel that 1 plus sine and get whatever you needed produced. So you see these problems, you really need to try. You might get to the dead end, and then you redo this again. One can say, Alex, you know what? What you have here is a numerator and denominator, you have a reciprocal, right? So I wasn't careful, I think, because my right side is actually with a minus. I can see here minus, you see this? And I put a plus. So, oh, that's no good. That's okay. So you can just put 1 minus here, because it's 1 minus, right? So on the top will be everything with 1 minuses. So let me use another color. See, you can always discover your mistake. Just main thing is don't panic. So it's 1 minus here. So it'll be 1 minus here, 1 minus here. So then what you're going to cancel is 1 minus, not 1 plus. And that way you will get exactly what you need. So you say, Alex, you're kind of fixing your answer under this. In a way, because you need to always keep in mind what is that you're trying to produce. Because if you don't pay attention, who knows where this is going to bring you. And that's why the point is always keep attention to what you're trying to produce. So I need to get 1 minus over 1 plus. So that's it. Looks like I got it. And that makes me feel much better because we just produced it. So I guess the main point of all of that is get plenty of room. So because if you start to look at more of these, they get in pretty crazy. So you might do them for a while, and that could be pretty time consuming. And that's why I'm not asking you to do this. I can still try one because I really enjoy them. But again, you might be stuck with this for like half of a day when you have nothing else to do though. But anyways, you see there is letter V here also. That's something that doesn't appear too often, right? Maybe I'll try one with V. Let's see how this is different in here, because everything else has status, right? So first of all, I'm going to get to share a separate board with you because it looks like there are lots of writing here. So copy this here first. So 77. What I have to prove is that on one side, we've got secant V minus tangent V, secant minus tangent. And that's squared and then plus 1. How about that? And on the bottom, I got cosecant V. How would you like that? Cosecant V multiplied by secant minus tangent. Secant minus tangent. And this is supposed to be equal to 2 tangent V. So on the right side is pretty straightforward expression. So I don't touch the right side. I'm going to work with this so-called left side, so it looks more complicated. So I'm going to keep simplifying it. So the question is, how can I do that? Well, looks like that secant V minus tangent V squared, so that numerator I definitely want to try to tackle. And I'm just going to square this stuff, I guess. I'm going to say I can write this with sines and cosines. Secant is 1 over cosine, tangent is sine over cosine, so maybe that'll give me some more pleasant things. So let's do that. So secant is 1 over cosine V, subtract tangent, which is sine over cosine. See, I went that route because I have same denominator, and that will be nice to handle. So what's with these? Well, I also gonna write them with sine over cosine because I think that way I'll be consistent with my numerator. So it's cosecant, which is 1 over sine. So you should be familiar with what cosecant is, what secant is. Otherwise, it'd be kind of tricky. And notice that that is same exact parentheses. So 1 over cosine minus sine over cosine. And that seemed to be a good start, but with no squared, right? So what's going to be next? Well, looks like I have on the top the fraction with denominator cosine squared of v, and numerator is 1 minus sine, which is also squared. Okay, and there is still plus 1 in here. And on the bottom is 1 over sine, and we have here 1 minus sine divided by the cosine. So I basically copied that cosine. So there is a product of two fractions that are kind of very different. They are pretty different. So what should I do next? Well, what bothers me here is having the complex fractions. So the next step, I think, will be good to actually take care of something happened with my choices of colors. I'm not sure what's going on. My new panel does not really have colors in it. That's pretty interesting. So anyways, maybe because I'm using this whiteboard. See, they just, oh, it's here. Actually, it's hiding. That's good that they have it. So my common denominator is sine, cosine, and cosine squared, right? So what I'm going to do is clear all of these denominators. So for that matter, I need to multiply it by cosine squared, which is cosine times cosine times sine. So if I multiply by that n on the top and on the bottom by cosine squared times sine, I'm not going to put v, it's too much already. And here's the same, cosine squared times sine. So everything is multiplied by that. So my goal is to make this look nicer. So sine, cosine cancel here. So nicer, so we're going to have just a numerator part. So the numerator part that remains will be a product of 1 minus sine times cosine on the bottom, right? Times cosine on the bottom. That's all we have left. And for a numerator, I think I need to distribute because this perfect square, so I can write it as a 1 minus 2 times 1 times sine plus sine squared. And this is also squared. How would you like that? Oh, actually, no longer squared. I just distributed. I just squared, right? So I'm going to distribute that sine and then have also that stuff. So what do we get? We get a mess. We get a sine of v minus 2 sine squared. See how crazy this exercise is, because it's really for what? It's just practice manipulating various things. And now I better take a look at what my goal is. And my goal is 2 tangents. So it's 2 sine over cosine. So that's what I want to get. So it looks like I already have over cosine. So this all has to somehow cancel and give me the only sine in there. So how can I possibly cancel this, right? Notice I was just distributing something like sine over that parentheses. So I need to get 1 minus sine. So they will cancel, multiplied by another sine. So that's my goal. So first of all, you notice that sine could be factored out, and that's good. So let me continue here. So sine will be factored out. That's what I need. So what's left? I have 1 minus 2 sines of v and plus sine squared. I think I'm missing something. I'm missing this guy, right? Because there's a more. Ah, I see this. That's what I was wondering. There's this thing. 1 times cosine squared times sine. Cosine squared times sine. Okay, so now I feel better. So it'd be sine squared, and there's also plus cosine squared. So little by little, we're getting closer. That's the feeling I have here. And looks like we can put now this two together. Remember what the sum of these two guys is? It's number 1, right? And this is just awesome because looks like we indeed getting the 2 that is coming out somehow. I don't know how yet, but at least we've got a 2 because this one and that one is already 2, right? So actually it just came out. And what's left on the bottom, I just copy 1 minus sine times cosine of V. So looks like this stuff patiently waits for me. Sine over cosine, that's my goal, actually. And what's left over is 1 minus sine that I will try to cancel. And what's up here is 2, look at that, minus 2 sines. Oh, just what I need. Factoring out 2 from the top. You see how messy this thing is? That's why I'm saying that you don't want to worry about these exercises because you just keep doing it, and eventually, yes, you got what you needed. So what's left is exactly what they say we're supposed to get. So it's a sine V, and then 2 I put in front, and then cosine on the bottom, and that's exactly the goal, right side here. So I think we all should have a break after that because it's just too much, right? So my goal is not to make you panic or tell you that you're going to have exercises like this on my tests. I think it's good that you see it. And if you can follow it over weekend, it'd be just perfect. But of course, I'm not going to expect you to get to this because it's very tedious, lots of algebra involved. But that's what you're going to have if you decide to take that differential equation class, because you'll find all kinds of derivatives and then you're going to need to factor, cancel. It's exactly this kind of work. And that's pretty tedious, I guess. So if you like this, then you know what would be the class for you. So you take Calc 1, Calc 2, and I guess that differential equations you can take after that. Calc 2 is prerequisite. But anyways, let me go back to share our screen that we used to have. So I guess section 7.4 will be concluded at this page, so I don't think you want to worry about them. And then we're going to see various other identities for trigonometry, such as in 7.5, you have another, I think, 6 coming on you. And some of them are very popular, so I will discuss them next time. So anyways, I'm not going to give you a quiz today. I'll let you go and enjoy weekend. So I stop this. If some